Okay, so I told you I was going to a 3-day crash course in open science that was organized by the Open Science Center in the LMU, and there were a lot of people giving talks that belong to the SORTEE, which is the Society for Open, Reliable, and Transparent Ecology and Evolutionary Biology. Yeah, so I will tell you what the lectures were, and they were from reproducibility crisis to open science, so looking at the history and how open science started. That was by Tim Parker, who is at the moment, I think, the president of the SORTEE organization. Then what is credible research and how workflows achieve reproducible data. And that was given by Malika Ile. She is part of the Open Science Center here in the LMU. We look at the open data, how important it is in order to guarantee transparency and reproducibility. That was a speaker, was Dominique Roche, or Roche, I don't know. He has been doing some cool analysis on this whole idea of being or doing open science. Is it good or bad for scientists, and is it improving or not? So how open science affects the daily lives and the research of people who are trying to do or are following some of the open science principles. Then we had a talk about biases in research and how to avoid them, which I am really not well. I don't know that much about them. I know they exist, but to be honest, they are like, all the information that I find about biases is like in psychology. So I think this talk helped me a little bit. And the speaker was Rose Odia. And Wolfgang Forsmeyer, who made emphasis on statistics. And we heard about research data management basics that was done by the LMU library, and was telling us about the services that are offered. So, in general, what is exactly the reproducibility crisis? This is a problem that was discovered, or it was already known, but it was never spoken out loud. And people started to do analysis of how often do you try to reproduce data published by other group and you cannot reproduce it. And that is a problem, because when you're publishing science, you want to say that that applies in all cases. And it was not happening. So it did start the analysis of how systematic this problem was. They did it in psychology, but it was reported later on by all different disciplines: medical, biology, physics, everywhere. So there is no no escape. And mainly some causes have been named, and this is basically the academic system and how it works. So how does it work? The more papers you get or more publications, you have better chances to get a permanent job, or keep your job, kind of. Then the more papers, that means as well that there is a lower emphasis in quality of documentation, because it has to go fast. And the journals are part of the problem as well, because the journals and the editors are focusing on selling their journal. That means they have a preference for showy science over science. And that is a problem. So what solutions came up after the problem was recognized? The solution basically that we have at the moment is the concept of open science. And what does it mean? That we all have to have open access to the data. And not only the data, but as well how the methods, which methods were used to analyze the data. And that allows us to reproduce results, or at least find out, if we're not able to reproduce the results, find out why might be the case. Because it doesn't mean that the other lab is wrong. It's just that little things that were maybe not documented are relevant for the assays. Sometimes, believe me, sometimes even the lot of some of the components makes a big difference. The other solution is that to promote a verification process by funded organizations and journals. That means you have to send your data, and the journals and the funding organizations have to really verify that you did follow the guidelines and open science. Then it came out, so okay, you shared your data, but sharing the data is not the same as sharing the data. That doesn't mean that everybody will understand what you shared. You can put it so cryptic that nobody will understand what you did. For this reason, now there are some guidelines to consider that data is good and like reproducible, and those are the fair data principles, which I will tell you in the next slide. Pre-registration, which is measured to avoid p-HARKing. I will tell you later about what we were doing is identify biases, and if we identify it, we can deal with them if they are avoidable, or at least we know which ones they are. If they exist and we cannot deal with it, but we can make kind of like interpret our data, always consider that they might be biases. So FAIR is just for findable. That means everybody can find your data, and usually your data is placed in a repository so that everybody can have access to it. And most important is that you put as well metadata, which metadata is just the data about the data. It's the data that describes what kind of data you are using. Then it has to be accessible. That means everybody can access the data and metadata file formats, and use it independently of the operating systems and software access. All these principles, because we are working all the time with computers, it applies not only that it's understandable by people, but as well understandable by machine. That means you can have formats that a machine cannot read. Then we have the interoperable, which is the use of standardized data formats. And that way everybody knows that the same type of information is in all the different data sets that are published regarding a certain aspect of science, and they can be structured or unstructured, but basically we all are able to use it. And the R is for reusable. That means we have data and metadata. Usually we'll have a license, and this license that we are using is the Creative Commons. There are different types of licenses, but the idea is that you give the right to other people to reuse it, and by reusing it we're able to advance science, because we don't have to start from the beginning. If somebody already has the data and has published some data, you can build upon that. The pre-registration, I told you that is a solution for p-HARKing, but what exactly is p-HARKing? And this is what people do, kind of. So you have a hypothesis you made and you do the experiments, but there are unusual results, and you said, no way we can publish this as it is right now. The editors will never take it. It's not a positive result, so you will not get it. But you are able to create some hypotheses based on that unusual results. So you twist these unusual results after you have proven your new hypothesis, and you said that your initial hypothesis was all the time, all along, was this new hypothesis that you created based on those unusual results. and you publish it like that as interesting results, and you do not say about the fail results, fail kind of, because they are not fail. It's just that they gave way to a new hypothesis. It's not fail. That's what it is about, is to explore, and we do our hypothesis based on previous results. And by not showing what maybe did not work as we thought it will be, you are not mentioning the whole process, and that doesn't help anybody. And that is what is called p-HARKing. Now, what is the idea of the pre-registration and how it is solving it? So now, with the idea of pre-registration, is that you make a hypothesis based on your literature research, as you did before, and explicit, you say what data you will collect and consider and why, and which one you will kick out. Then you will say exactly what data analysis methods you are planning to use, and all this goes into a document. And this document is uploaded. This document is the pre-registration, and is uploaded in the repository that I know about. Is called the OSIF, or Open Science Foundation. And you upload the document and you register the study. In the moment that you register, you get a DOI, which is a digital object identification, which makes your pre-registration unique. And at the same time, you get a timestamp when you pre-registered. Then people are sometimes concerned that they will be scooped. Scooped meaning somebody will steal their ideas and try to do it as fast as possible so that they will publish first. But you have the option to hide it from the public up to 4 years. And in those 4 years, you work in it, and then you publish your research and including the pre-registration, which you can make available to the reviewers. Or you can use it to apply for what is called a registered report, which means you tell a journal who has this type of publication, I have this idea, I'm going to do it in this way, as I wrote in the pre-registration. Do you want to publish it? And some of the journals right now are accepting that, because they kind of like review or pre-review your paper and validate that the science is sound. And then they said, okay, good. When you have 1 year or 6 months, depending on the journal, to give us the results of this, what you just presented, and we guarantee that we publish it. What helps is that you can have as well negative results, what is considered negative results, but you will get the results published. That means everything will be available for the community. And all this process is to avoid what was done before, that is, you try to sell the pretty and showy science, omitting how the process was, which is helpful for everybody. Good. So that's about the pre-registration. Now about biases. So first I have to define what a bias is. And what I found was the definition is a systematic error introduced into sampling or testing by selecting or encouraging one outcome or answer over others. And we are humans. We are bound to have those biases. If we are aware that can happen, then oh, okay, I will try to avoid that. To be honest, I'm still learning about it. So it's one of the things that I haven't had too much time to get into it. And as soon as I know more, I will let you know. Here are the things that I learned this time. And from the theory that I learned, the importance of simulated data. I mean, in all the tutorials for R and Python, I always saw how to simulate your data. I'm like, oh, I don't need that. I'm always getting data. But now I understand why simulated data is important, because you need to create your analysis before and simulate the data so that you know that your statistical analysis are good. Or see which failures might have, yeah, and try to repair them or consider them when you are doing the analysis or your conclusions. I learned as well about the LMU library, what kind of services are offered. So one is the repository services and one is the data management services. And practical things, I did know that Git is version control system where you can work together, and I've worked together already, but how this collaborative work in GitHub works. And yeah, we did some exercises in statistics, and I think I have a very good idea now, or a much better idea on how to detect typical statistics mistakes in biology. Even though they were focused on behavioral biology and ecology, which is a little bit different for what I do, because in some of the experiments of behavioral biology, you have very few data points, like 100 birds or things like that. But when I'm working with data, I'm working with a million data points, sequences, or maybe 20,000 genes that are in the human genome. So the size of the sample is different, and there will be different parameters that are needed for statistics, but it was really nice to see what the typical mistakes are in biology and how to discover them and what the effect is really in the analysis. So that's kind of like it. For those who need hard data, so statistics, I will be looking at some publications that might help you to look at the benefits and really the effect in publications and careers and all the stuff when you do open science. I think open science is an excellent idea, and I've seen how the old method or the old way of science was being done, or is being done, sadly, and that's why I want to change it, and at least I want to start in my lab completely with open science. So I hope you enjoyed the overview about what open science is, and yeah, see you next time. Okay, bye.